talk's just basically going to be about a few examples of the techniques that are currently being researched, and sort of more empirical, simpler techniques that can be used to quantify extreme beach erosion. Okay, so I'm going to set up a few examples, maybe 4 examples, and all these are going to be based at a case study site over in New South Wales, Australia. So we're going to be looking at Narrabeen Beach in Australia. So this is a sort of 3.5 kilometre embayed beach, just about 20 kilometres north of Sydney. So it's very exposed to the South Pacific Ocean. You can see here this extends right out into the South Pacific. And at Narrabeen Beach there was extensive wave data and beach profile measurements have taken place over the years. So we had access to about 25 years of wave data time series. So that's 20-minute intervals of significant wave height and significant wave period, and about 30 years of profile measurements. So these 30 years of profile measurements are at these different locations down the beach here. And all the work we talk about today is going to be based on this profile 4 in the centre. So the beach, because it's embayed, it's subjected to a wee bit of beach rotation, so there's some longshore movement, although the sort of long-term trend is relatively stable. So picking profile 4 in the centre here is the most, is the least influenced by this longshore sediment transport, so it's the most stable. Okay, so overall, it's a pretty, because of how exposed the beach is, it's subjected to a very high energy wave climate. So because of that, you've got a mean wave height of approximately 1.5 metres with a mean wave period of about 10 seconds. And that results in highly variable morphology. So this is a plot of all the beach profile measurements at profile 4 over this 25-year period. So you can see that the range of variability is almost 300 metres cubed per metre in this single profile 4. So it goes through, transitions through a number of beach states very, very rapidly just because of the wave climate and its location. So overall, the linear regression in that plot shows a sort of generally slight decrease in the beach volume over the 25-year period, but it's sort of too short of a measurement to make any sort of long-term assessment at what's happening. But there's a slight decrease in the beach volume, although it is affected slightly by these cycles of beach rotation. So this is a picture of Narrabeen Beach that I stole from my website. This is just after a storm, and it just sort of goes to show you how much recession can take place in these storms. So it's usually quite a steep beach anyway, but the actual profile usually extends much more further seaward than this. So this is a post-storm beach profile, and you can just see how steep the berm is there after the erosion from the storm event. So it just sort of tries to give you an idea of how variable this location is that we're going to be talking about. Okay, so the first sort of simplest estimation technique that you can use is just making empirical estimations from the beach profile measurements. So the procedure for that is you have these long-term measurements of the beach profile. From them you can determine the reduction in volume between the consecutive profile measurements, and then you can use the same sort of techniques as you would to estimate extreme flood events or extreme wave heights or whatever. You fit those estimated erosions to an extreme value. So you fit an extreme value distribution to the erosions from the profile measurements, and then you use the fitted coefficients to then estimate extreme return periods for erosion. So we're lucky enough at Narrabeen, you can only really do this if you've got a location that has enough profile measurements over a long enough period of time, so say 20 plus years, to actually have confidence in your extreme estimation. So this is just an example of this. The top, we've done it in 2 different ways. The top's an annual max. So these are the annual maxima beach erosion that have occurred in 25 years. And the bottoms are peaks over thresholds. So the red lines are threshold level, and the red dots are all the erosion volumes that fall into that extreme threshold. And these are the results here. So the top's using the annual max, a generalized extreme value distribution fitted to the annual max data. And the bottom is using the generalized Pareto distribution fitted using the peaks over threshold technique. So the first thing you'll notice about these are the confidence intervals, probably. So the confidence intervals for the annual max are much larger than they are for the generalized Pareto distribution. And this is just because of the peaks over the difference between peaks over threshold and the annual max technique. So a lot of you might be aware of this sort of stuff because it's relatively straightforward, but the main disadvantages of the annual max are your fitting values, so this value here, for example, and then one towards the end that aren't true extremes. So it's taking it into account non-true extremes when it's fitting the parameters, therefore its estimations don't have as much confidence as they do when more extreme values are used, and certainly at the lower end of the scale, at the smaller return periods as well, the annual max don't give us good values because it's using non-extremes, whereas using peaks over threshold, all data can kind of be said to be extreme values. So you have much more confidence in your fit, and you probably have a better representation of the erosion volumes at the lower return periods. So the next possible technique you could use is something you'll be a bit more familiar with, and it would be using a 1 in n year storm event. So when you talk about flooding or you talk about coastal erosion or things like that, you focus in on these 1 in 100, 1 in 200 year storm events. So the next thing you can do would be to generate a 1 in 100 year storm event, use a numerical model or an empirical model to then generate an erosion volume, and that erosion volume would be your 1 in 100 year erosion level. So the first thing you have to do to do that is to identify all the independent storm events in the wave data time series. So you identify all the independent storm events in the wave data time series. So for Narrabeen Beach, this is what we have here. This is the peak wave height of all the storm events. Oh no, sorry, I should say this is we're having a bit of a problem with the animations in some of the slides. So there should have been a slide here explaining what sorry, there should have been a figure here explaining what an independent storm event is. Okay, so what happened at Narrabeen is we determined what changes in the wave climate introduced erosion. So at about a 3 meter wave height, that's when the beach started to erode. So an independent storm event were when the wave heights grouped together above 3 meters for a prolonged period of time, and when they had an independence of 48 hours between the next storm events. That was a single independent event. So this is a time series of those events. So there's approximately 22 a year at Narrabeen Beach. That's 1 every 2 weeks. That partially explains why the morphology is so variable, because you're getting a lot of these high energy events that are making these big changes to the beach. So next, once you've identified the storm events, what you have to do is calibrate the numerical model for that. So in this instance, we're using this model XBeach. So a lot of you might be familiar with XBeach. It was a joint venture by UNESCO, IHE, TU Delft, and Deltares, and it's a 2D storm erosion model. So it sort of specializes in estimating and modeling dune erosion. So from your previous independent storm event time series, we picked 4 different events that result in different levels of erosion. So all these events are slightly different. Some have got high peak wave heights, some have got long durations, short durations, trying to get a decent spread here. And we set up the model to give the best representation of the erosion induced by these events. You can see that there in the dotted profile. Unfortunately, this was meant to be another animation, so you just have to believe me that the results are actually pretty good, and that the model can be set up pretty well for modeling storm-induced erosion at Narrabeen Beach. So the next step then is to go back to your empirical storm erosion time series and generate bivariate dependent return periods for each storm event. So a 1 in 100 year storm is not necessarily just a 1 in 100 year wave height. It has to take into account the duration as well. So if you fit the peak wave height and the duration to the generalized Pareto distribution using a peaks over threshold technique, and you fit that to a logistics model to get the dependency, you can come up with these bivariate return periods of peak wave height and duration. So then what we did was take 5 of these at each return level and model them using XBeach to estimate the extreme erosion volumes. So these are the results. The black and grey lines are the empirical erosion. So this is taken from the measured profile data again, just using 4 different techniques to get a decent spread of values. And the red line is the maximum erosion at each return period generated by XBeach. So you can see here that it's a pretty good fit through the middle of the measured profile data, but what is interesting to note is that the 1 in 100 year erosion level is actually less than the estimated sort of 1 in 25 year erosion level from the empirical data. So this shows a major limitation of using a 1 in n year designed storm event. And that limitation was touched on last month by Dr. Harshini Karunaratne at Swansea University, who was discussing the impacts of storm clustering. So what happens when you get storm clusters are successive erosion events will essentially pick up. So the next one will essentially pick up where the previous one left off, and the erosion will continue. So a 1 in 100 year storm event doesn't necessarily give you 1 in 100 year level of erosion, because it depends what has happened before that. So again, we don't have an animation here, unfortunately, but this is just a wee a recap. So these are storm clusters that you can see that have happened at Narrabeen Beach over a sort of 15-year time period. And what we did with these storm clusters were we determined the power of those clusters and the erosion that occurred during those clusters, and we compared that to the erosion that occurred during single events that have roughly the same power. And what you see is that during storm clusters, so same power but smaller return periods, you actually get more erosion than you do during individual storm events. Storm clustering is very important when it comes to trying to quantify beach erosion. So this whole thing was kind of progressed by a group in these guys down here, Dr. David Callaghan in the University of Queensland in Australia. So he came up with this modelling methodology that's called the full temporal simulation. So the procedure, the full temporal simulation, it's a combination of a statistical model and an empirical model that estimates dune erosion. So this is the procedure here. It's sort of based on some of the stuff we just discussed previously about fitting the independent storm events to the generalized Pareto distribution and using the logistics distribution to get the dependency between them. It also has a distribution that allows you to estimate the peak wave period for that as well. But the key here is this non-homogeneous Poisson process. So that's fitted to the spacing between the events. So that allows you to generate a synthetic storm climate that has the same temporal variation as the historical data. So these guys generated that and using a Monte Carlo simulation, and it was also looped with this empirical dune erosion function. So they generated a random storm event, they determined the erosion, then they determined what happened, what the next storm event would be and when it would occur. They took that, generated a wee bit of recovery, and the process was looped like that, so you get this sort of full time series modelling of dune erosion based on a synthetic storm climate. So this is an example here of just what the statistical model does. So I've just done this for 100 years, and you can see here you can generate this time series of synthetic storm events for whatever length of time you want. So within that, they determine the erosion and the recovery between these storm events, which allows the modelling to progress into a time series. And these are the results. So it's a pretty good fit for the majority of the measured profile data up to about a 10-year return period. But the thing about this is it then sort of shoots off very quickly. So your extreme values at 1 in 100 years are very high. So one of the main reasons for this is this empirical function that they've used to estimate dune erosion. So because it has no physical processes or things like that, it doesn't allow, during large storm events, it doesn't allow for a sort of new equilibrium condition to occur, and that the rate of erosion to slow down. So it just sort of gives you a value for the volume that's been eroded. So at the higher end return periods, these might be slightly unrealistic, but there's a pretty good fit at the lower end return period. So the next step was what we did at the University of Glasgow, and it's a statistical process-based approach. So it's using the exact same statistical model as what the group in Australia did. So you use the wave data time series, use the same statistical modelling techniques to generate storm climate of however long you want. But then what we tried to do was to use a fully process-based numerical model to make these predictions. So rather than using an empirical technique that just gave you a volume, we used the XBeach model to hopefully try and give a fuller representation of how the beach actually changes during these time series. So what you have to do here instead, in addition, sorry, is XBeach is primarily a dune erosion model. So in order for it to model these long-term time series, you have to set it up and allow it to also simulate beach accretion. So then you can divide your time series into erosion and accretion periods. You have two different XBeach setups, and the time series modeling can progress like that. So depending on how you set up the parameters, you can actually get XBeach to change the sort of predominant direction of sediment transport and morphological change from offshore, because it's always wanting to move things offshore because it's set up and designed as an erosion model. So if you set up the parameters slightly different and you account for different physical processes, you can switch that so that it then moves things onshore. So these are the results for a 29 and a 20-day period where the mean wave height was small, so there was no storm events. The mean wave height is just over a metre in both these cases. And you can kind of see what's happened here. You have the pre-recovery, so a fully dissipative beach stage, so it's all been eroded away. Then after 29 days, you have this big, fully reflective berm that's been accreted back on. And you have the same here for this 28-day period. And if you set XBeach up in a particular way, you can get pretty good skill scores for both these periods during the accretion. So once you have these two different setups, you can then sort of run them together and do some time series modeling with XBeach. So we saw how well it worked for a period in 1981 and 1982. So this is a full year. That full year was divided into erosion and accretion periods. This is using the storm threshold. So then using the calibrated setups we discussed earlier, these periods were modeled in sequence, and you can check things like this. Is just you could check it. The benefit of this is you can sort of plot and analyze anything. So you could look at the shift in contour positions. You could look at the change in volume. There's various parameters. You've got a lot more flexibility than you do with the other empirical techniques that we were talking about. So this is the beach volume for a year. The solid black line is set up using the previously calibrated accretion model that I just showed you. So you can see it's not bad actually, even the solid black line, but it does overestimate the volume and overestimates the rate of recovery. So one of those is, one of the reasons for that is it's just shifting between a sort of fully eroded and a fully recovered state. It doesn't account for anything in between. So in order to try and get a better representation, we set it up as best as possible just to give this the best fit to this annual volumetric trend. So the results are actually pretty good. It follows the general trend pretty well, and you can see the erosion and accretion periods in the annual cycle there. So to assess its suitability in longer term simulations, we set that up for 100 years. So we generated a synthetic storm climate of 100 years and modeled that in series using these XBeach setups. And then these are the results here. So that the black line at the top is set up using the single event calibrated accretion model, so the one that overestimates the rate of accretion. So because it overestimates the rate of accretion, there's much more sediment on the beach, so the rates of erosion are much higher, and you get this higher estimation of beach erosion at the various return periods. The red line is using the model that was calibrated over 1 year, so it gives a better representation of the average conditions that are likely to occur at the beach. And you can see there that the results are much better than the event calibrated one, although they're still maybe a wee bit too high at the higher return periods there. Okay, so just to kind of conclude, this is a comparison of all the methods here. So the main thing that jumps out is, although this FTS was the first sort of fully storm climate modelling methodology available, and at the low return periods, it's actually the lowest of all the techniques, and it also increases at a rate that's much higher of them. So although the methodology in the FTS is probably sort of cutting edge and what you want to try and do, there's a limitation with using these empirical functions, because you don't really get the full understanding of the processes that are happening during these erosion events. So what's also interesting is a one in using a design storm event actually ends up with the lowest extreme value. So the lowest extreme value, this is only for a 10-year return period, just because that's what the more detailed one goes up to. So you get a lowest extreme value at the 10-year return period using these design storm events. So that sort of highlights the limitations in them, and the fact that it doesn't really include clustering of events and the merging of erosion events into one. The other interesting thing to note is the POT. So this is probably the simplest, although you need a lot of data to do it. This is probably the simplest methodology, and it actually performs pretty well compared to the other ones. So this is just a case of having erosion data available, provided that erosion data is provided that profile data is representative of erosion. It does give you a pretty reasonable, quick estimate of what your extreme values might be. So I think that's us done. So I'd just like to say thanks for paying attention and listening. So if you've got any questions, I'd be happy to try and answer them. The tidal range there is about 1.5. The spring tidal range is about 1.5 meters. So I think I can go back. So there's two. The middle line there is the mean water level, and then that's the spring tidal range. So it's about 1.5 meters. I think the threshold wave. Yes, the threshold wave condition was stuck to define storm events. So that's one of the main limitations of this, that you're assuming all your erosion takes place during these storm events, which you're absolutely right. That might not happen. You also might get accretion during higher waves, higher wave heights, depending on where they come from. So it is one of the major limitations in that. Can you explain the selection of your thresholds? Thresholds for the extreme value modelling? Yes. Yep. Right. So the thresholds for the extreme value, I mean, it's sort of, as you know, it's sort of up to you to decide that. So a lot of people just go for the sort of 95th percentile. Anything above the 95th percentile is extreme. But these are based on a mean residual life plot of the data. So if you plot the mean residual life plot, you get this sort of plot with different trends in it, and there should be a distinct linear section within that. And usually anything within that linear section should be a suitable threshold. But there's a bit of judgment, you should maybe try out a few and see how it fits. But these were based on doing that, and so picking a value, picking the lowest value within this linear section, and just seeing how well it fitted the data, basically. Well, the practical value. So the practical value, it's more if you're looking at sort of beaches that are affected by storm erosion, and these are important for recreation purposes or whatever, and you're looking to implement shoreline management plans or beach nourishment plans or things like that. So all these things cost money. Putting in volumes of sand costs money. So if you can sort of accurately quantify what's happening at different return periods, you can get a much better idea of how much nourishment you're going to need and how much that's going to cost and how often you're going to have to do it and things like that. One of the most sort of practical things as well is if you have forecasting wave climates, so techniques like this, you have a forecast for wave climate or different forecasts over the next year, you can get a rough idea of the trends and what's likely to happen at the beach. You can compare that with putting in sort of hard defences and seeing how that changes the erosion volume and things like that. So the sort of the final technique gives you a bit more flexibility to be able to see what's going to happen. Allows you to change parameters in the beach and maybe design your management plans a wee bit better. That help? Yes, if you use XBeach to predict, you still need measured data to calibrate, but that doesn't have to be over such a long period of time. So you could essentially, go out during one winter. If you've got a decent forecast, you could go out during one winter if you've got the flexibility and just measure pre and post storm profiles. So you still need to calibrate the model, correct? But it's a much shorter period that you're interested in, so you don't need it for say 25 years. You maybe need a year to see how it's responding annually, but if you only really need to set it up for the storm erosion, it's much shorter periods. Well, no, my next step isn't a shingle beach actually, but there's Dr. Karunaratne at Swansea and her colleagues are working on sort of trying to do a similar sort of approach in the UK. So, but I think that's in a sandy beach at Liverpool Bay. But very recently, actually, there's some guys at Plymouth that have developed X Beach so they can model gravel beaches pretty well. So this is all X Beach is primarily a sandy beach model, but it's now been extended into gravel beaches. So it'll be very interesting to see how that responds to sort of real test cases. Okay, thanks.